By combining knowledge of linear algebra, we can relate the geometric properties of complex numbers to those of two-dimensional vectors. The real and imaginary parts of a complex number correspond to the two elements of a vector. Complex addition corresponds to vector addition, where adding the real and imaginary parts of one complex number to the corresponding parts of another complex number is equivalent to adding the corresponding elements of two vectors. According to the rule of complex multiplication, we expand the algebraic multiplication of two complex numbers and then convert the result to the vector representation form. Then we convert the complex number c plus d times I on the right-hand side to an equivalent vector representation. At this point, the left-hand side complex number, a plus b times I, is not a vector but a matrix. As a complex number acts as an operator, it performs rotation and scaling on the object being operated. Therefore, based on linear algebra experience, we can easily obtain the equivalent matrix for a complex number as an operator. Finally, we use matrix multiplication to verify that the two calculation results are equivalent. We can convert the result of complex multiplication into an equivalent matrix form. In this form, both complex numbers are treated as operators, and their multiplication corresponds to the superposition of two operators. We transform them both into equivalent matrix operator forms. The original multiplication of the two complex numbers is equivalent to the product of two matrices. According to the rules of matrix multiplication, the calculated matrix is completely consistent with the matrix of the result of complex multiplication. Matrix representation or binary tuple representation can better reflect the essence of complex numbers. Imaginary numbers are not imaginary, and complex numbers are a special case of matrices in two dimensions. Here we summarize the equivalent vector and matrix representations of complex numbers. We also have the equivalent vector and matrix representations of the imaginary number I.